Good morning, students. So today we will do one question on the topic of binding energy. This is a very important topic. Please do a lot of numericals on binding energy. Also, when you do numericals on binding energy, please ensure that you understand the mole concept very well. These two, the concept of mole and the binding energy numericals, come in combination, both the concepts get used. So today what we will do is a reasoning and assertion question on binding energy per nucleon and especially focusing on the graph. So let's start discussing this question. You can see the question is pertaining to reasoning and assertion, right? So let's see what is exactly is the question. So the question says nuclei having mass number about 60 are less stable. Okay. Reason: when two or more light nuclei are combined into a heavier nuclei, then the binding energy per nucleon will decrease. Alright. So I hope you have understood the question. It is about stability of the nuclei. So one of the things you need to understand when you do these questions is your understanding of the concept of binding energy. Now, to calculate the binding energy, what are the steps you take? Okay. So the first step that you take is always is to find the mass defect. Okay. So first step is always to find the mass defect. Okay. I'll just pick the pen. So you pick up the pen and so first find the mass defect. Once you find the mass defect, multiply this mass defect with C square. You get the total binding energy of the nucleus, and then you divide it by the number of nucleons inside the nucleus, which is the sum of protons and the neutrons. Right? So you get binding energy per nucleon. And the graphs that you see, right, are essentially the binding energy per nucleon versus the number of nucleons in the nucleus. So first of all, understand that how to calculate the binding energy using this formula. This is the binding energy. This is your mass defect. Now, let's come to the stability part of it and discuss it before we start answering it. So first of all, let's revise the concepts. This is your graph of the binding energy per nucleon versus number of nucleons in the nucleus. So as you can see, this graph shows stability, maximum stability at iron. Because the question is about stability, right? So we have to understand this graph. Actually, you need to memorize this graph to be able to answer a lot of questions. So this is your iron, which is the most stable. On this side and on this side, something else is happening. We will discuss that. Now, if you notice, the binding energy of iron is almost 8.5 here, right? It is the highest. And another stability zone is this helium, okay? Helium is also very, very stable. So it is not exactly following the graph, but it is still stable, like iron is very stable, right? So helium is also very stable, a one-off exception in the graph. Okay, and then you can see the binding energy is reducing on this side. The binding energy is also reducing on this side. So essentially, if you notice the region of, when we say less stable, right? The less stability is happening on the left of the iron and on the right hand side of the iron. So these are the regions. So this particular uranium is very unstable, we will say, because it is on the right side. This is the peak of stability. Uranium is slightly less stable. You can see the binding energy of the uranium is approximately 7.5. And you can see even these on the left hand side of the iron on this side are also unstable. So it is all about stability. This graph is an important marker of stability of the nuclei. Now let's revisit the reactions that take place in radioactivity, right? So the nuclear reactions, fission, right? What it does is it breaks the uranium into two parts. I think one is 95, the other is 235 minus 95. And then the nucleus keeps on, the daughter nuclei, which comes from uranium, the 95 and the other one, they keep on breaking until they reach iron finally. See, every nuclei uh, which is unstable because it has low binding energy. Uranium has low binding energy. So it wants to go into a more stabler zone. Once you go into a more stabler zone, you are becoming iron. That's your main goal. And even from this side, right, everybody wants to become an iron. So here the fusion reactions happen. Okay, so lower side is fusion. This is also less stable, less stable. This is also less stable. Everybody wants to, have more binding energy per nucleon, and they want to become like iron, which is around 56. So let's read the question. Okay, the question is nuclei having mass number about 60 are least stable. In fact, this is a completely incorrect statement because we are seeing that iron being somewhere close to 60, right? If I draw a line here, it would roughly be around 60. Actually, it is 56, I think, is actually highest stability situation. So this is completely incorrect. I think this should be most stable, right? Now let's look into the reason why he says it is so. When two or more light nuclei combine into a heavier nucleus, then the binding energy per nucleon will decrease. Wrong. So he's referring to two light nucleus, which is the fusion side, right? You can see these are light nucleons, right? Maybe first 20 or so are light nucleons. These are heavy, right? These are heavy ones. Lot of protons and neutrons. So the ones which are in the first 20 range are not very stable. They combine together and result in fusion, and they start becoming a larger parent nuclei, or say the daughter nuclei, for example, becomes larger in the reaction. So we are not discussing fusion reaction. We are discussing a nuclear process which is called the fusion. Fusion means two small nuclei are combining to become a larger nuclei. Because of what? Because the larger nuclei is more stable. The binding energy per nucleon increases. He says they combine because the binding energy decreases. Never. Everybody wants to attain the highest level like iron here, right? So you want to be an iron at the highest level. You don't want to be a less stable nucleus. So I hope this is making sense to you. Very, very important kind of questions for your board examination and general understanding. A lot of theory questions come on this graph. So study this graph very carefully and understand that some part of the graph is more suitable for fission reactions. The other part of the graph is more suitable for fusion reactions. And everybody wants to be at a high binding energy per nucleon, not at low. So uranium, for example, has lower binding energy than iron. And you can see these, the first 20 especially, the binding energy is very low with the exception of helium, right, which is very stable. So you can say helium is an exception. That could be another question to you. Helium is still stable, although it is a smaller light nuclei. Okay. So I hope this made sense to you and you were able to understand. So our answer is the assertion is incorrect and the reason is also incorrect. So I hope this helped you. Please don't forget to watch my playlist on nuclei and atomic physics, which is a chapter of atoms. You will find a lot of questions pertaining to the concepts which are there for JEE Mains, for your for the nucleus and stuff like that. So thank you very much and wait for my next video.